Alright, so far we have been talking about ionic compounds and writing formulas for ionic compounds. But I'm sure you remember that there are other types of compounds, particularly molecular compounds, where we see covalent bonding. And we'll get into that more next chapter. But what exactly is a molecule? And what compounds contain these molecules? Well, a molecule, as you see there, is an electrically neutral group of atoms that act as a unit. Our polyatomic ions are a group of atoms with a charge, but a molecule is electrically neutral. And we see these in molecular compounds, but again, you can also know them as covalent compounds. And here's two examples. The water molecule, very common, most common molecule on planet Earth. But you see we've got two hydrogen atoms and an oxygen atom combined. Here with sucrose, there's 12 carbons, the black ones, with 22 white hydrogen ones and 11 red oxygen. So you can see in a molecule that you actually see the number of atoms that are connected together. And ionic compounds, we were reducing that and talking about a formula unit. We'll review that here very soon. There are actually seven elements that exist in nature as molecules, particularly diatomic molecules, meaning two atoms together. And here we see the 7 elements: hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, and chlorine. Now you do want to remember these because when we write chemical equations and balance chemical equations and everything like that, we need to make sure we're using these formulas for these 7 elements. So the way that I remember them, and maybe you will too, is this fun little phrase, Hofbrinkel. Hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, and chlorine. So there are the 7 diatomic elements. So make sure you know those. So again, what exactly is a chemical formula? Well, it's going to show us the kind and numbers of atoms or ions in the smallest representative unit of a substance. On planet Earth, water molecules exist, little molecules where there's 2 hydrogens and an oxygen attached. And that's what a molecular formula shows us. It shows us the number of atoms and the kind of atoms in the representative unit. Our ionic compounds, again, are our formula units. It tells us the ion ratio. Nowhere on planet Earth do we see one sodium ion attached to one chloride ion. They're always found in these crystal forms, and the formula gives us the ratio of those ions. On paper, they look the same, but a molecular formula tells us the actual number of atoms combined together. The ionic formulas show us the ratio. So how are we going to know if we have a molecular or ionic formula? Well, that's what this chart is going to help us with. Ionic compounds, they have a very high melting and boiling point, and because of that, they exist pretty much as crystalline solids at room temperature. Very sturdy structures. And so if you went home and if you put sugar and salt in 2 separate pans on your stovetop and cranked up the heat, the sugar will start to melt. The salt would not melt. Your stove doesn't get hot enough to melt the ionic compound sodium chloride. Now, ionic compounds must have a metal and a nonmetal because we need a positive and negative ion to come together. Our metals form the positive cations. Our nonmetals form the negative anions. Are there exceptions to this? Of course. Ammonium, for example, is a polyatomic ion, NH4, with a +1 charge. Well, and nitrogen is a nonmetal, so is hydrogen. So we can have ionic compounds without a metal. But as a general rule of thumb, we need to see a metal and a nonmetal. So any formula that has a metal and a nonmetal is representative of an ionic compound. And again, these formulas are a formula unit showing us the ratio of the ions, not the exact number of atoms in the molecule, which is what we'll see here with molecular compounds. So our molecular compounds, they have low melting and boiling points. So mainly they're liquids or even gases at room temperature. So like water is a liquid, oxygen, carbon dioxide, nitrogen, those are gases at room temperature. There are a few solids, um, sugar, for example, plastics, but they do melt pretty quickly at a pretty reasonably low temperature. Ah, yes. Girls pass notes, boys pass gases. I was just showing liquid and gas. I'm so funny. Now, our nonmetals are forming the molecular compounds. So our molecular compounds are made from only nonmetals, and their formulas give us, again, the actual numbers of atoms in the molecule. So again, that's sucrose, 12 carbons, 22 hydrogens, and 11 oxygen atoms actually bonded together to form that molecule. Now, since we're in the naming and formula writing, we do have a special group of compounds, acids. They will give off hydrogen ions when dissolved in water. We will do a whole unit on acids and bases in the third quarter, but they are definitely a type of compound, and we'll need to make sure we know their names and formulas. We use a lot of them in the lab between now and then. Acids can be very corrosive, especially when they're very concentrated, so they can dissolve metal as well as your skin, but I try not to give it to you in that strong of a concentration. And here are some common acids and their formulas that we should know. Hydrochloric acid is in your stomach, so that's a pretty important one that we need to know. Carbonic acid and phosphoric acid. Read any soft drink label and you'll probably see one, if not both of those. Sulfuric acid is the world's most produced and used chemical. Nitric acid, also extremely important in industry. And acetic acid is found in vinegar, apples, gives it that smell. So you'll notice you will need to know these formulas and their names, but they're pretty easy. Hydrochloric has chlorine in it. Carbonic acid has carbonate in it. Phosphoric, phosphate. Sulfuric, sulfate. Nitric, nitrate. And acetic has acetate in there. So again, you should be able to match up those names and formulas, and we will be using them quite often throughout the year. Now, molecular compounds. We haven't done much with their formula writing, but they're actually pretty simple. On your friend the flow chart, you have a list of the prefixes. So again, your friend the flow chart, on the back of your ion card, there is this list of prefixes that we can see down in the lower left-hand corner. And this is used with molecular compounds. And so we can use these prefixes to write the formulas for many molecular compounds. So essentially, when I read the name of the compound, I can write the formula. So for example, disulfur hexachloride. Looking at my list of the prefixes, di is 2 and hexa is 6. So disulfur hexachloride is 2 sulfurs and 6 chlorines, both nonmetals. Trihydrogen pentabromide. All right, tri is our prefix for 3, penta is 5. And so I have trihydrogen pentabromide. Now there is one little exception, and on your friend the flowchart, it says there that you don't need mono with the first element. So if our first element only has one atom, then I don't need to say monocarbon. So carbon monoxide is CO. I do need the mono with the second element, but I do not with the first. So you've probably heard of carbon monoxide compared to carbon dioxide that we exhale, which is CO2. But carbon monoxide, again, you don't need mono with the first element. And then our last one here, tetraphosphorus dinitride. Tetra 4, di again is 2, so P4N2. And you'll notice with molecular compounds, even though it looks like you can reduce those formulas, you don't. because the molecular formula tells us the number of atoms combined. So there are 4 phosphorus and 2 nitrogen atoms covalently bonded together. Our last little notes piece here says, why is it necessary to have a systematic method of naming chemical compounds? Well, when chemists are working with chemicals, they need to know exactly what is in them and what they're made of. And especially like with medicines, if you research stuff, on TV it says Prilosec or Zoloft or Paxil, but they all have a chemistry name as well, which identifies the stuff that's in there. So common names do not tell us anything really about what the composition of things is. Soap is a chemical. Chalk is a chemical. Chalk is calcium carbonate. Well, chalk doesn't really tell you anything, but calcium carbonate means, hey, there's calcium in it, there's carbon in it, and there's oxygen in it. Because, of course, carbonate is CO3 minus 2. Bleach. Bleach is sodium hypochlorite. All right? That's also what they use to put chlorine into pool water. So when I say bleach, you don't know. You say, hey, it kind of smells chlorine-y, and that's because there is chlorine in there, sodium hypochlorite. And so those systematic names give us a much better idea of what chemicals are involved in the compounds. And again, as it says there's way too many compounds existing to give them all a special name. So we will investigate naming compounds a little further here in our next videos, but that concludes the notes.